In this lecture, I would like to highlight some very beautiful interplay between combinatorics of Young diagrams and the presentation theory of GLN. For that, let me first recall a little bit what we know about representation theory of Lie algebra GLN. We know classification of all reducible finite-dimensional representations, and it goes like that. We have a bijection between the following sets. One is all elements lambda. So these are tuples consisting of n complex numbers. So this lives in Cn. And so this lambda i's, they satisfy the following property. Lambda I minus lambda j is, first of all, it's integer, but it's also non-negative integer. So this is one set. And another set is, of course, isomorphism classes of irreducible finite-dimensional representations of GLN. And bijection goes like this. So, of course, if I have an element lambda in here, I can denote by the corresponding irreducible finite-dimensional representation by L lambda. And L lambda satisfies the following properties. It is generated from a single vector by action of GLN. So I write inverse enveloping of GLN acting on some vector V, where we have the following properties. So V is skewed by all upper triangular matrices. So Eij is a matrix with 1 on ith and jth place and 0 everywhere else. So Eijv. So this one is actually 0. For I less than j, and Eiiv is lambda I v. This is for all I from 1 to n. Okay, so this is a very quick review of classification of finite-dimensional representation, irreducible finite-dimensional representations of GLN. They are labeled by such things. We will need a little bit smaller set than this one. So if this set we denote as P plus, say, GLN, so we consider the set P plus, which is P plus GLN, intersect with, so we're not taking some lambdas from Cn, but we would like also all these pairs, lambda I are called pairs, to be integers. So and also non-negative integers. So let me write it like this. So I would only consider elements like this. So if I have an element lambda that lives in here, then I can put into correspondence to this element what's called Young diagram. Young, sorry. Diagram. What is a Young diagram? Now each lambda I here is, since lambda lives in here, is a number, and it is non-negative integer. So therefore we can draw such a picture. We can draw rows of boxes of some length, and so these boxes will be aligned by the leftmost box. So here they are aligned. And number of boxes in the first row is lambda 1. Right? Since lambda 1 is a non-negative integer, it makes sense to count how many boxes is here. And number of boxes here is lambda 2, lambda 3, and so on. On the other hand, if I'm not starting with any with some element from P plus, I can just consider independent notion of Young diagram. It's a diagram, again, consists of rows of boxes, which are aligned by leftmost box, and number of boxes from top to bottom do not increase. So this is called Young diagram. Of course, if I have Young diagram with at most n rows, I can consider the corresponding element of P plus. Okay, and so actually irreducible finite-dimensional representations labeled by lambda from P plus, they're also labeled by Young diagrams with at most n rows. Okay, so now these are already very important combinatorial objects, but let me introduce more. Let me introduce what's called Young. Let me introduce what is called Young tableau. So Young tableau, and I will abbreviate it as YT. And sometimes I will need to specify what's called shape. So Young tableau of shape lambda, and lambda is an element in here. And when I specify the shape, I will write something like this. It is the same as Young, so it is the same as Young diagram of lambda filled with numbers these are numbers, consecutive numbers from 1 to some fixed m. So we take Young diagram, fill it with letters of some alphabet. In our case, our alphabet is the numbers from 1 to m. And we fill it with whatever, no rules for now. And such thing is called Young tableau of shape lambda. Okay, so for our needs, we will only take, we will consider only m equals to n. So why do we need all this? So we would like to use all this combinatorics of Young tableau and Young diagrams to realize finite-dimensional reducible representations corresponding to lambda from P plus as a quotient of a k-fold tensor product of tautological representation. And we will construct some very good basis in this quotient. Okay, so let me fix some number k. It is a natural number, so it's integer and it's positive. And consider the following GLN module. The GLN module V bar, which is, well, as I said, I take Cn. This is what I call tautological representation, and then I consider k tensor power k of Cn. So I take Tn tensor Cn, and so on, k times. Okay. All right. So now I would like to fix also lambda from P plus such that number of boxes in corresponding Young diagram, which I denote by the following, like, and this actually is sum of lambda i's as I run from 1 to n. I would like this to be so number of boxes to be equal to k. Very well. And then for any so now let me give you the rule how having a Young tableau of shape lambda, you can give me a vector in V bar. This is a very natural construction. So for any Young tableau T, so of shape lambda, define vector Vt. This one lives in V bar as follows. So I would rather draw a picture. So my T is boxes filled with numbers, right? Mm-hmm. So I have a picture like this. What stays in this box, I will denote as I1. And then I number fillings in the boxes consecutively from left to right, from top to bottom. So I2 lives in here, I3, and then I4, and then I5, I6, and so on. So I7 in here, 8, 9, 10, say. So k equals to 10 in my example, right? Then Vt will be, so I take, so my V has a standard basis. So say E1 is a vector with 1 on the first place and 0 everywhere else. And E2 has 1 on the second place and 0 everywhere else. So I take to the first factor, tensor factor, I put EI1, and then to the second EI2, and then I just continue, and on the last I will have EI10th in my example. So this is my how vectors correspond to Young tableaus of shape lambda. Okay. So now, obviously, if I consider all VTs, where T are all Young tableaus of some fixed shape lambda, this gives me the basis of V bar because I can fill it with whatever numbers, following whatever, without any rules. Let me now, so as I said, I would like now to take L lambda and present it as a quotient of V bar by something. Well, so let me now introduce this something. So let R lambda be the subspace of V bar spanned by the following elements. By the following elements. So I will have a lot of elements, but they will be of 3 different types. Type 1 is the following: V corresponding to Young tableau, such that to all Young tableaus, such that T has 2 equal entries in a column. So what I'm writing here is that I already gave you a lot of vectors. So I consider all possible Young tableaus such that at least in one column I have 2 equal entries, and they can be together or spread apart. Doesn't really matter. I put such corresponding vector into my subspace R lambda, and all linear combinations of such vectors are also given here. Now, what else I throw in there? Throw the following sums: Vt plus Vt prime, where T and T prime differ by switching 2 entries in the same column. Differ by switching 2 entries in the same column. And this is not it. So I promised you 3 types, and type 3 is all vectors corresponding to of this form: Vt minus sum over some other Young tableaus Vs, where the sum is over all exchanges so let me put it in the quotation marks, and I will need to explain what is an exchange. But in exchange, is some operation with the Young tableau. If you give me two fixed columns, so between two given columns, of t, and a given subset of boxes in the right column, right chosen column. So this is okay. This is hard to write in words. I would rather give you an example. Okay, so consider maybe just two columns. And maybe my tableau will be like this: 1, 2, 3, 4, 5, 6, 7. So I need to choose two columns in my T. Since I already have only two columns, there's nothing. There's one choice: this one and this one. Then I need to choose some subset in the right column. So it means that, well, let me choose this one and this one. So where 2 and 6 is. Then an exchange is when I choose any two boxes from the left column, say 3 and 7, and interchange it. But I need to interchange I need to interchange actually keeping the order. So 2 should be on the top and 6 on the bottom. So the exchange in this case will be, so let me again draw this Young diagram. So 2 goes to here, 6 goes to here, and then 3 is exchanged with 2, 7 is exchanged with 6, and everything else is on their places. So this is an example of one exchange, but here it's I have a sum, right? So I can put this 2 and 6 in any place in this column consisting of 4 boxes, in a way that 2 on the top and 6 on the bottom. This is the only rule, right? So in total, I will have 4 choose 2 choices, exchanges in this sum. Okay. So this is the most non-trivial thing, but I throw all vectors of such sort. So I give you T, any Young tableau, then consider all exchanges, write such a sum, form such a vector, and this will be in R lambda, and all linear combinations of vectors that I just gave you in item 1, 2, and 3 for me R lambda. Okay. Of course, so this is an interplay between not only between combinatorics of Young diagrams and representation theory of GLN, but also interplay of representation theory of permutation group and Lie algebra GLN. So the permutation group or symmetric group which we need here is a group of permutation of k letters. So it acts naturally on V bar. So how does it act? Well, V bar is has k factors in tensor product. So Sk actually permutes these tensor factors. And also I can write R lambda in such a way. So I just take V bar, and it is an image of particular elements sigma of what's called group algebra. So let me first write a formula. So it's the sum, and sigma is from some subset S tilde, right? And S tilde, so for some S tilde subset of C of Sk. So what is this thing? So you just think of, so Sk is a group, right? So you permute and you can compose permutations. But you can now, instead of group, consider linear combinations of, so instead of group, you can consider algebra, where multiplication is given by group operation. So this is algebra with a basis given by elements of a group, and multiplication is given by multiplication that we had in the group. Okay. So all this is some formalities to say that I would like to see that R lambda is actually a representation of GLN. It's a sub-representation of GLN inside V bar, right? So for that, I would like to argue that it is actually some over images of V bar under some elements from C of Sk. Why do I need this? So actually, action of GLN on V bar commutes with action of Sk. Right, so therefore if I take some element x from GLN, and I consider x like image of its action on R lambda. If I use this form of R lambda, I can write down it's a sum over C from S tilde sigma of V bar, and x acting on here. So x commutes with action of Sk means that actually I can, pull this through, and it will be sigma acting on x V bar. But x V bar is just V bar, or it is inside V bar, I should rather say. So therefore, this is inside R lambda. So this means that if I act by some element from GLN, it's still inside R lambda. So therefore, R lambda is sub-representation. So you might also ask why Sk, action of Sk commutes with action of GLN. Well, you just need to remember how GLN acts on V bar. Just remember a formula and see that this formula is, actually is the same if I try to permute tensor factors in V bar. It's just formula stays the same when I permute tensor factors. Okay. So the punchline is that R lambda is a subrepresentation of GLN, so therefore I can quotient by R lambda. And the theorem that I would like to prove, at least maybe partially prove, is that L lambda is isomorphic to V bar by R lambda. Before maybe proving the theorem, let us see two particular cases that we already know from the first semester. Examples. First case is that if lambda corresponds to the diagram which is given by a row of k boxes, then actually L lambda, as we know, it is so it means that we have it is a representation of highest weight with k on the first place and 0 everywhere else, and we know that it is given by kth symmetric tensors of Cn. And indeed, so let us indeed see that this is V bar quotient by R lambda. So we quotient by what? So in each column we have only one box, right? So therefore there are no types, type 1 and type 2 vectors in R lambda, right? They all were concerned about two entries in the column, so there's no such cases in here. So, but number 3 actually says that exchange here boils down to just switching boxes in the column. So if I take some filling of this row of boxes, right, VT, then in exchange I just need to pick 2 boxes and switch them, and then it will be minus VT prime, where T prime differs from T by switching 2 boxes. So all vectors like that, they span R lambda. So therefore I quotient by, so it just means that in V bar I add additional relation that says that if I switch 2 boxes, right, it will correspond to the same vector. It is exactly the symmetric tensor power of Cn. And the second example that we also know, or should be familiar for at least somebody. So okay, it is when lambda corresponds to Young diagram, which is a column corresponding to k boxes. In this case, L lambda. So this is representation of highest weight of this sort. So where I have k here, right? So therefore, and this is okay. This is I take as a prerequisite. It's a exterior tensor power kth of Cn, right? So these are anti-symmetric tensors. Okay. So what is this? What can we see that it is actually coincides with the construction that we just introduced? So indeed, all these exchanges make no sense because we have just one column. We cannot choose two columns. So exchanges, we don't have them. But number one and number two in the generators of our lambda says that, okay, if I have two equal entries, that the corresponding vector Vt is just 0. Or if I choose two entries and switch them, then I make this vector Vt plus Vt bar, Vt prime equal to 0. If t from t prime, they differ by switching to entries. So it just says that I quotient, when I quotienting, I add a relation such that if I switch two boxes, I get minus sign. So this is exactly antisymmetric kth power of Cn. Okay, so this is so what I'm doing now is a generalization of these constructions that we saw when we constructed representations of GLN. Okay, proof of theorem. Proof. How can we see that some representation is actually a reducible representation corresponding to L lambda? We might find singular vector, the vector which is killed by EIJs where I less than j, and then see that this singular vector is of weight lambda. And then, well, this vector should be not 0, but also we would, after that, we know that L lambda sits inside V, this quotient. But then we would like to compute the dimension of this quotient and compare it with the dimension of L lambda. If they coincide, then they are the same. So okay, let me see what might be the single vector in here that generates everything. Okay, so I introduced the following Young tableau. So I fixed the shape lambda for the proof of this theorem. And then I just take my diagram, lambda, and fill numbers like that. In the first column, I will put 1s. In the second, 2s. And then 3, and so on, 4. And if I have more, I proceed in this way. I need to. So I claim. So okay. Let me let Vt bar denote the image of Vt. So Vt is vector in V bar, but I would like to consider this image after quotienting. So the image in V bar quotient R lambda. So I claim that Vt. So first of all, I claim that Eij acting on Vt0 bar gives me 0 if I equals to j. So we would like to see that. This one is actually, so how, if I have an element of GLN, say x, right, in GLN. How does it act on, say, so x? How does it act on V1 tensor, so on tensor Vk? So V1 tensor v1 and so on vk some elements in Cn. Well, it acts by Leibniz rule. So I take x v1, tensor v2, and so on, plus v1 tensor x v2, and so on, plus and then you continue. So then x on v3 and so on. So it means that if I take eij action on vt0, so that means that I have a bunch of terms, and in each term my eij acts on a corresponding box, right? And in this box, so eij acts on the standard basis as follows. If it maps ej to ei and everything else to 0. Okay, so therefore I can write something like this. So let me just check for e12. Acting on vt0 bar. So I can write the following. So it's v bar corresponding to the following. So it affects only, so this e12 seeks for boxes with 2 in them, right? Otherwise, so each box corresponds to a tensor factor, if you remember, right? And number in the box correspond to the label in the standard basis that corresponds to this factor, right? So e12 acts on e2 only by non-zero. So it looks in the tensor factor for e2s which correspond to number 2 in the box. So therefore it takes each box with 2 and replaces it with 1. So it is here, it is 1 plus v bar, and then it takes it seeks for another box with so 1, 2, 3, 4, 1, 2, 3, 4. Another box, so say this one. So we have 1s in here, and then I have 2 here, but this one it replaces with 1, and then 2, and so on. And each time vt0 is given in such a way that each time when we do this, we will get 2 1s in one column. And under our relations, all these vectors become zeros. So therefore, this is the 0. On the other hand, what is EII VT0? So again, EII seeks for boxes with I in them. And then it takes this box and replaces again with I. So it doesn't change anything, but it gives me a bunch of terms, which are just the same vector. And the number of these terms is the same as the number of boxes with I in it. So it will be number of boxes with I times vt0 again. But the number of boxes with vi is exactly the length of row I, which is lambda I. So this is lambda I vt0 bar. And so vt0 bar actually, if this vector is not 0, this gives me a single vector of needed weight. Of course, I checked for E12 here, but for Eij, for I equals to less than j, for others, similarly. Okay, so let me maybe remark at the end why this VT0 is not 0. It's not so easy to see, but if it's not 0, then we know that. Okay, let me actually denote V lambda to be V bar quotient by R lambda. So provided that VT0 is not 0, VT0 bar, right? We have that L lambda is inside V lambda. But we need that it is actually equal. So we need to compare dimensions somehow. So dimension of L lambda we know, actually, because we know characters, we know the character formula, and we can compute this dimension. But dimension of V lambda, for that we need some basis, or at least some spanning set. And this is an important construction of today's lecture, is how to give the spanning set, or actually basis it will be a basis eventually of V lambda. For that we'll need notion of semi-standard Young tableaus. Definition. Semi-standard Young tableau Young tableau is Young tableau with entries increasing along rows and strictly increasing along columns. So this is the definition, and this is some subset inside Young diagram, Young tableaus of a fixed shape. Okay, so proposition is that okay, we would like only keep VT bar where T is only semi-standard Young tableau, and actually it happens that if we keep only that, then we will end up with a basis. But at least let us prove that it is spanning set, that it is enough to keep only them. Okay, proposition. The following set, let's call it B, VT bar as T is semi-standard Young tableau of shape lambda. Right, so semi-standard Young tableau I abbreviate like as SYT. So such thing is okay, so this spans, let me erase that. V lambda. So remember that V lambda was this quotient. Okay, let's prove that. So take any t. This is Young tableau of shape lambda. So yt of shape lambda. So the idea is the following: we take vt bar, or rather without bar, we take vt, and sorry, with the bar, and try to write it down as a linear combination of vs bar, where S only belong to semi-standard Young tableau. Okay, so how to do that? The first step is that we actually order columns in the right way. So Vt is plus or minus Vt1 with bar, where T1 has increasing, let me put it like that, increasing columns. Okay, so again, so let me write it again. Vt bar is plus or minus Vt1 bar, where T1 bar has an increasing column. So this is because we have such a relation such that if we switch reorder boxes in columns, we'll get the same up to sign, the same vector up to sign, right? Okay. Next, we'll introduce the following order. So introduce an order. It's actually total order on on the set of Young tableau of shape lambda. I will give it just schematically. So this is, suppose this is your Young tableau. And these are columns. Then I order boxes in a not very usual way, from bottom to top and from right to left. So like this. So this one is the first one, second, third, and fourth, and so on. Like that. And once I ordered them, I can, once I have an order, each Young tableau corresponds to a tuple of numbers, right? And these tuples I can order corresponding to alphabetic order. And then, so let me put it like that, and then alphabetic order. Okay. So if my T1 happen to be not semi-standard Young tableau of shape lambda, then, well, we have such a situation. So again, schematically, I can draw it like this. In some columns, say again, this is my Young diagram. Then maybe more here. But what's important that in some row, right, I have two elements, A and B, such that A is greater than B, right? This means that T1 is not in semi-standard Young tableau if I have such a situation, like a wrong situation when my I have so I have not increasing filling of my boxes. Okay, but then we have this relation of exchanges that, so then VT1 is bar, is plus or minus sum over VS bar. And these exchanges we do for these chosen columns, C1 and C2. So we found the place where we have this bad situation where A is greater than B, since T1 is not necessarily T. And do all exchanges with these columns, and we fix a subset of C2. So we fix two columns, and we need to fix a subset. And subset is the following. It's B and all boxes on the top of B. So where S, so where S is obtained from T1 by exchanges between columns C1 and C2 and subset of boxes in C2 given by all boxes at the top of B. So this B here, right? So let me write it like this. Anyways, it's harder to write down. I explained it on this. But in this sum, corresponding to this order that I introduced, we have that S is greater than T for each S in the sum. Okay. So making an exchanges, right? We actually increase the tableau first of all, but then okay, we if it happened to be that in our sum again we found something which is not semi-standard Young tableau, we do this operation again and again. But since there's only finite number of tableaus, at some point this process will stop, and we'll have only semi-standard Young tableaus left. Therefore, at some point, we will just express VT bar as a sum over VS bar with where S is only semi-standard Young tableau of shape lambda, and therefore we proved the proposition. Okay. So the only thing which is left is to play with dimensions and see what we have. So let us summarize what we have so far. So we have that the order, the number of semi-standard Young tableaux of shape lambda, it is greater or equal than dimension of V lambda, right? This is because we have spanning set B of this size, and dimension is, of course, if it's the basis, then dimension is equal to this. Maybe it's not the basis, we have more vectors there, then dimension is smaller. So this is follows from proposition. On the other hand, we know that L lambda sits inside V lambda. So therefore, this is greater or equal than dimension of L lambda. Right? So this is by proposition. So therefore, we need to check that number of semi-standard Young tableaux of shape lambda equal that dimension of L lambda. Right? Then we just collapse all this sandwich. We will have the dimension of V lambda is the same as dimension of L lambda, so therefore they are equal. On the other hand, we will know that this is equal to the dimension of L lambda, means that we constructed a very natural basis, which is labeled by semi-standard Young tableaux, very studied combinatorial object, and you can compute stuff using these objects. So therefore, the question is, can we compute the number of semi-standard Young tableaux? And if we can't, is it equal to dimension of L lambda? Okay, so again, question. S YT lambda, the size of all semi-standard Young tableaux of shape lambda, is it equal to dimension of this or not? Of course, it is, but how to see that? So for that, we need to remember what we know how to compute dimension of L lambda. So for that, we would like to see, recall what is character of L lambda. So character of L lambda, well, by definition, it was sum over dimension of weight subspaces, right? And then, so mu here are tuples of integers, actually, positive, non-negative integers. And then, so character of L lambda is a polynomial in this case in n variables. And so it is spanned by monomials, x1 to the power mu1, x2 to the power mu2, and so on. And coefficient is the dimension of weight subspace, right? So L lambda of mu, let's recall, it is all vectors v in L lambda such that E I acting on v gives me mu I times v. So this is for all I from 1 to n. So this is just definition of actually any character, but we know Weyl character formula, which says that character of L lambda is Schur polynomial, which is, let us recall, it is given as by the following formula: determinant of x j to the power lambda I plus n minus I. So this is a matrix corresponding of with ijth entry, which is given by this, right? Over determinant of the same thing which is written on the top, except lambda I here should be 0. So xj n minus I. So this we know from representation theory. Okay, but it is also known the following fact. So theorem S lambda can be written as follows. It is a sum over T, which is semi-standard Young tableau of shape lambda, and of which terms x, let me write and then I explain what it is. X to the power weight of t. So what is this? So first of all, weight of t, it is okay, it's tuple of elements of non-negative integers depending on t, mu1 of t, mu2 of t, and so on. And here mu I of t is number of i's, number of entry I in the tableau T. So you just count all boxes where you have I inside this box. And then x to the weight t is by definition is x1 to the mu1 of t, x2 to the mu2 of t, and so on, xn to the mu_n of t. So theorem is the following. You take S lambda, which is defined by this quotient. Then you can, it is a very combinatorial statement. So then you can write it as a sum like this of monomials given by weights of the corresponding semi-standard Young tableau of shape lambda. Okay, so this theorem we will prove on next lecture. But let us see why this theorem implies this equality. Well, from this line, we know that actually dimension of L lambda, right? L lambda is a direct sum of all weight subspaces, all its weight subspaces. So therefore, dimension of L lambda, it's sum over all mu's dimensions of L lambda of mu. And this is you just need to put x1, x2, all x's to be 1, right? So this is character of L lambda where you put all x's equal to 1, right? On the other hand, we can use this theorem and now we can, so L character of L lambda is the same as S lambda. And if we put all x's to be 1 on the right hand side, so S lambda, and I put all 1's, right? So each term here is just 1. So it will be sum of 1's over all semi-standard Young tableaus. Of shape lambda. But of course, it means you just count how many semi-standard Young tableaux are there. Right. So we can actually continue. So this equals to this. So therefore, this theorem implies this equality. Yes. So right. So we proved everything except this theorem that will be proved in next lecture. And except one more thing. So why v t0 bar is not 0. So let me explain that, and then we will end the lecture. For that, it is pretty non-trivial to see, but let me just point out how one can do this. Okay, you can of course see this in a straightforward way, or actually you can do it in this way, which actually opens up some insight. Why do you have all these relations in R lambda? And two of them are pretty natural, and the third one with exchanges. It's quite strange. So introduce variables Zij. Here I runs from 1 to n, and j runs from 1 to k. And also consider the following elements of polynomials in these variables. So I take D. So these elements are labeled by a bunch of indices, and this is a determinant of such matrix. So Z1 I1 in the first row, and then Z1 IP here, and then in the second row you will have Z2 I1, and then Z2 IP, and so on. And then in the last row you will have ZP, so it's P by P matrix, and it's a determinant of such thing. Okay. And then if I have T Young tableau of shape lambda, and say, so again I need to label entries somehow. So labels of the first column will be I1 1, I2 1, and so on. So upper index corresponds to column. So I1 1, I2 1, and so on. In the second column, I will have I1 2, I2 2, and so on. And okay, you got the idea. Then introduce corresponding element dt. It's a product over columns of T. And for each column, I put in, there is a factor in here of this sort. So di1 j, and then, sorry, and then I2 j, I3 j, and so on. So for each column, I will have a factor, and I have a product over each column. So this is my element polynomial corresponding to a Young tableau T. And I claim, so lemma, which I will not prove, but I will indicate how it helps us to see that Vt0 is not 0. Vt bar, if I put into correspondence Vt bar dt, is extends to a linear map, a well-defined linear map. What you have to do to check this, you just need to check all relations that are going on in R lambda for these strange polynomials. And so, of course, so what did we have there? We have that in each column, if I switch to entries, I will get minus sign. This is exactly property of determinant. And also, if I have two equal columns, that is 0. This is number 1 and number 2 as types in R lambda. But what about exchange relation? So exchange relation for dt is given by what's called Sylvester's lemma. So actually, all this strange, process that we introduced, like combinatorial, it's actually something that is going on with just matrices of variables. Okay, so this is some linear algebra, and exchange relation that we have in terms of dt's, in terms of these polynomials, translated as what's called Sylvester's lemma. I will not give a particular some concrete formulation. I will just call names, and you can check how it's related by yourself. But anyway, so the statement is that such correspondence is actually a well-defined linear map. On the other hand, you can check that dt0 is not 0. This is easy to see. Just check that each determinant corresponding to one column in T0 is not 0. It is because all columns are different. But since dt0 is not 0, well-defined linear map cannot send 0 to not 0. So therefore, Vt0 is not 0. Vt0 bar. And so this lemma, this construction, proves that that Vt0 is actually a singular vector. It's not 0 vector. We didn't kill this by adding relations that are lambda. So okay. So this kind of concludes everything that I wanted to talk about in this lecture. And okay, thank you very much.